Example 6. In a chemistry experiment, a liquid is heated and its temperature observed. The graph shows the temperature of the liquid in degrees Celsius, T minutes after the experiment starts, up to the end of the experiment. So if that's the end of the experiment, we can see from the graph that it goes for 10 minutes. They heat up the liquid, and obviously if you heat it up, the temperature is going to rise. Now the temperature is rising linearly. It's a straight line. Question A. State the length of the experiment. Oh, we already said that. So it's 10 minutes. The graph shows the temperature up to the end of the experiment because that's what it says here. So the experiment lasts 10 minutes, from 0 to 10 minutes. Estimate the initial temperature of the liquid. 20 degrees. Right, if you have a look there, that's at 20. Well, that's 80 to there, right? So every line is 10 degrees. This can be read off the graph by looking at the point at which t equals 0. Well, that must be the beginning of the experiment because t equals 0, the start of the experiment. The point 020 is the t-intercept of the graph. So that's going to be where it's crossing the y-axis. In this case, it's the temperature axis. C. Estimate the rate of change of the temperature of the liquid. Answer, 30 degrees per minute. The rate of change is the same as the gradient of the line. The line passes through the point 020, that point, and 280. Okay, they've just read that off there. Remember, you want to look where the line passes through the grid lines, right at the corner. So they're using those 2 points, that point and that point. You could choose any other point along here that was easy to measure. You could choose that one, 8 and 260. Right? You could have chosen that one. But they chose this point and that point. The line passes through the points 020 and 280. So the gradient is y2 minus y1 divided by x2 minus x1. That's 60 on 2, which is 30. And that's why it's 30 degrees per minute. Now, how do we know it's degrees per minute? Because that's what the ratio is. The top is degrees, because that's this axis. And the bottom of minute is minutes, and that's this axis. So it has to be degrees per minute. D. Suggest a formula to model the variable t in terms of time. And this is the suggested formula right here. From the graph, this is clearly a linear model. So it has the form t equals mt plus c. That's the same as saying y equals mx plus b. You found c in part B. That's the 20, because it's where it crosses the y-axis, in this case the temperature axis. So we can put 20 in there. And you found m in part C, because part C asks for the rate of change. We know that's the gradient. The gradient's 30, so it must be 30t. So that's of the form y equals mx plus b. Its temperature, that's the y-axis, equals 30 times t, which is the x-axis, plus 20. That's the equation of that line. And it's a straight line. We can only do that because it's a straight line. We can put that straight in using y equals mx plus b form. Okay, this is part of the same question, but it's a change into the question a little bit. A different chemistry experiment lasts 8 minutes, right? The previous one lasted 10 minutes. A liquid is heated and its temperature rises at a constant rate. The initial temperature of the liquid is 40, and the final temperature is 320. Find the formula for T in terms of T, the time for this experiment. Well, they told us the initial temperature of the liquid is 40, so that's when the time is 0, so we can put the 40 straight in. We now know 2 points. We know 040 is one of them, and the final temperature is 320, so we know the point 320. If the temperature rises at a constant rate, then the process can be, and now that's important, the constant rate. It's written here, that we have to have a constant rate for this to work, right? Because it has to be linear. Then the process can be represented by a linear model. So T equals mt plus c. The temperature equals the slope times the time plus c. We are told that when T equals 0, the temperature equals 40. Okay, we wrote that in. And also that when T equals 8, the temperature is 320, the final temperature. Remember, it lasts for 8 minutes, so the point must be 320. Therefore, the point 040 and 320 both lie on the graph of this function. From the first point, c equals 40. Okay, we can put that straight in. Method 1. Use the gradient formula. M equals 320 minus 40, y2 minus y1 divided by x2 minus x1. That equals 35. Method 2. Substitute the point, 320, into the equation. You can put it straight into the equation. T equals mt plus 40. That's like putting it into y equals mx plus b. And then you can put t, that's 320, Okay, you're putting the 8 in here. Now, that's written the wrong way, really. Well, it's not the wrong way. You always should put the number before the letter. But don't be confused here. That T is the 8. So it's probably would have been clearer to put M8. We still don't know M. We're going to find M plus 40. So M equals 35. It looks the same M. That's how we got the 35 there. We have seen in example 6 that the same function equals mx plus c, right? So function equals mx plus c, and that's the same as y equals mx plus c, has been used to model two different situations. When the experiment changes, the formula changes. So if you change the experiment, as we just saw, from 10 minutes to 8 minutes, the formula changes because it's a different line. The equation of the line is different. The variables in this formula are x, the independent variable, and the function of x, or y, the dependent variable. In the equation, m and c are constants. However, for each different situation, the values of m and c may be different. They are called parameters. To define a linear function, you need to know the values of the two parameters m and c. Example 7. A water tank drains at a constant rate. It contains 930 litres of water, 3.5 minutes after it started to drain. It takes 50 minutes for the tank to empty. Let W be the amount of water in the tank, in litres, T minutes after it started to drain. A. Find a model for this function. That's water with respect to time. The amount of water in the tank at any time after it started to drain. Write down the rate at which the water tank is emptying. Okay, so this is the answer. So they've got the answer and there's their justification. That comes from the book. I've added this graph here. Okay, we've got the water here in litres. Okay, I need to write litres here. And we've got the time here in minutes. Okay, I've also added what we know. We know that at 3.5 minutes, it's 930 litres, because it told us that here. At 3.5 minutes, it's 930 litres. So we've got that point. The other point we know is that 50 minutes, it's empty. So that this value here would be 0, and that'd be 50 minutes. So we know this point and this point. We know it's constant. It says it's a constant rate. So we can just join those 2 points together. All right, and it'll look something like that. Now we expect it to be negative because the water is, as we increase the independent variable, the dependent variable is getting less because it's a negative slope. Well, we don't know that yet, okay? So we're still just drawing it, but we understand that the water is getting less and less as the time increases. So that's a definition of a negative slope. The rate of change is negative. So let's see what they've said over here. I'm drawing that, but we didn't really need to draw it. They didn't draw it. They just went ahead and put that down, and this is their justification here, and that's the other one there. Let me just move this thing. Good. So they put down this function is minus 20t plus 1,000. Okay, so this line looks good. It is negative, and also 1,000. We're expecting it to cross at 1,000. Still can't see that. Okay. Good. It looks like it will cross at 1,000. If we continue that right up to there, it's going to hit there at 1,000. And that makes sense because that's what that number means, doesn't it? That's the y-intercept, or in this case, the w-intercept, the function intercept. Now let's see their justification for putting that answer and also this rate of change. If the tank drains at a constant rate, and we can say that because it says it, then the amount of water can be modeled by a linear function. Okay, and so this is the model. The water, with respect to time, is m times t plus c, where these parameters m and c, as we saw, they're defined for this line. The information given can be displayed as follows. We know that at 3.5 minutes, it's 930, so that's that point. We know that at 50 minutes, it's 0 there, because they told us that in the question. And there's the points, 3.5 and 930, 3.5 and 930, and 50 and 0, 50 and 0. Substituting each point into equation 1, okay, we can make two equations because we've got two sets of points here, okay? We've got that set, we've got this one, and we've got that one. So what they did was they used this formula twice. They used it for this point, and then they used the same thing for this point. Okay, but they've done it, they've switched over the left-hand side and the right-hand side for some reason, a little bit confusing, but that's the formula there. So they've switched it around. It would have been good to keep 930 on this side. So what they're saying is that 930 on the left side equals m times 3.5. Remember, writing it like that looks a bit odd. Well, it looks, actually, it's correctly written. But as far as this formula is concerned here, it's better to probably write it putting the letter first because we know T, but we don't know M. We're trying to find M and C. So we put 930 there, okay, here on the left-hand side. And on the right-hand side, we put M, then we put 3.5 plus C. Now, they've switched sides, but that's still the same thing, right? And then they used this point, and they used 50 and 0. Now, remember, this 0 is a function value, so 0 equals M times 50 plus C. And that's why we've got 0 equals M times 50 plus C. Again, they've switched the sides. It's the same meaning, though. But again, it would be clearer if they wrote M with 50 after the M, because the 50 is actually T, because that's what we know. In that formula, we know the left-hand side and we know T. Okay, we've got two equations. Technology can be used to solve these simultaneous equations. We can put that in the calculator. Okay, there's a function in the calculator, the graphic display calculator, that can do that. A better way to do it, though, is to just use substitution. Remember, there's three ways to solve simultaneous equations: substitution, elimination, or graphically. Okay, here we have two choices. We could do it by elimination because the coefficient in front of C is the same in both. So if we subtract 1, or they've called that 1, we'll call this 2 and this 3. If we subtract 2 from 3, it's going to be 50m minus 3.5m equals 0 minus 930. And that would take out of this, the C would disappear then, because C minus C is 0. If you want to do it by elimination, that would be elimination. If you want to do it by substitution, then you've got this C here. So what you could do is keep the C here, move that to the other side, and you've got C equals minus 50m. Put in minus 50m here for C, and then also you could solve it. What you want to do is you want to get an equation with one unknown. At the moment we've got two equations, luckily, and two unknowns, so we can solve it. But you need one equation with one unknown to really find the value. And once you find one, you can then put it back into either, and you can find the other. So there, this gives m equals minus 20, and C is 1,000, and that's why they've got minus 20 for m and 1,000 for C. The rate at which the tank drains is given by m. That's why they've got 20 litres per minute. Now, why don't they have minus 20 litres per minute here? Because the word drains. Drains means get less than. So the tank drains at 20 litres per minute. That implies that it's a negative slope. It implies that it's a negative rate of change because of the word drains. Okay, continued. B, write down the amount of water in the tank when it starts to drain. Well, when it starts to drain, T is 0. Now, they've got 1,000 litres here. We know that from the formula because we know when T equals 0, it's 1,000. The function value is 1,000 litres. Okay. On the graph, we would just extend the graph up. The graph doesn't stop here. It obviously starts at T equals 0, so let's extend that. Okay, there you go. I've extended it up to there, and we do get 1,000 when it's 0. The formula, the equation of the line, and also the graph shows that at T equals 0, it's 1,000. So we've got that one. Then it says, C, use your model to find the amount of water. That's the model. This is just a graph. Use your model to find the amount of water in the tank after 30 minutes. Well, how do you find that? The answer is 400 litres because you put T equals 30 into the formula. So it's minus 20 times 30. Okay, that's minus 600 plus 1,000, and that equals 400 litres. Oh, there it is there. Great. And on the graph, of course, you could just, after 30 minutes, you go to 30 minutes and go up there, and we've got the same answer, 400. All right, exercise 5D. We've got 8 questions that are related to those two examples, and they look like a lot of fun.